Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we will continue our discussion of the canonical transformations from the paper Classical Mechanics. After studying this module, you will be able to understand and learn about the generating function of infinitesimal transformations. That is, while considering the canonical transformation, we will concentrate our attention on infinitesimal transformations because their generators are of great importance. You will learn further about the Liouville's theorem, which plays an important role in statistical mechanics. So, in Hamiltonian formalism, through some suitable canonical transformation, it is possible to render all the coordinates to the level of being cyclic. So, if you can find a suitable canonical transformation, the expression of Hamiltonian in these new coordinates, these new coordinates do not appear in the expression for Hamiltonian, then in such a situation the corresponding momenta are constants of motion. Moreover, there may also be a possibility of finding the canonical transformation for which not only the momenta, that both the momenta and coordinates become constants of motion. There also exists an important connection between the infinitesimal contact transformation and Poisson brackets. There is a connection between some suitable canonical transformations and gauge transformations, which of course is beyond the scope of this discussion here, and we will not say anything further about that. Since in Hamilton's formalism, the pair of independent set of variables qk and the generalized which are the generalized coordinates, and the set of corresponding conjugate momenta pk, they completely characterize the state of the system, then the phase space is a 2n dimensional space, and this is a space which is spanned by 2n coordinates and conjugate momenta. This is found to be invariant under canonical transformations. The phase space is invariant under canonical transformations. We start with infinitesimal contact transformations. The transformations that involve going from one set of coordinates and momenta, namely the set qk pk, to a new set capital Qk and capital Pk with the equations of transformations such that the new coordinates are functions of the old coordinates and old momenta and the time, and the new momenta some function of the again old coordinates and momenta and the time. Then if the transformation are such that the new coordinates and new momenta can be expressed by some equation in terms of the old coordinates and momenta, then such transformations are called point transformations. Now first consider an identity transformation. An identity transformation is that new coordinates are the same as the old coordinates, new momenta are the same as the old momenta. So let the identity transformation by generic function f2, which is a function of the old coordinates and new momenta, given by f2 is equal to a product of the old coordinate qi multiplied by the new momenta pi. Now from the transformation equations, the old momenta pi is the partial derivative of this f2 with respect to qi, which is equal to capital Pi, and the new momenta qi is the partial derivative of f2 with respect to the new momentum pi is equal to qi. So you see that this generating function f2 generates a transformation which are identical, that is, evaluates the old coordinates with the new coordinates and the new momenta with the old momenta as equal. So there is only a relabeling, and thus f2 generates the identity transformation Let us now consider an infinitesimal transformation in which the new coordinates differ from the old coordinates by just an infinitesimal amount. That is, the new coordinate qi is equal to the old coordinate qi plus an infinitesimal amount or infinitesimal chain delta qi, and the new coordinate pi differs from the old coordinate pi again by an infinitesimal amount delta pi, where delta qi and delta pi represents infinitesimal changes in the coordinates qi and pi respectively. The generating function will also differ by infinitesimal amount from the identity transformation we have discussed earlier. So the generating function can be written as f2, which is a function of the old coordinates and new momenta, as the sum of the product of the old coordinates and new momenta plus an infinitesimal amount epsilon times some function g of the old coordinates and new momenta, where epsilon is some infinitesimal parameter of the transformation. The transformation equations for the new coordinates given by the equation 22.3 earlier, and they become that the partial derivative of f2 with respect to qi, which is equal to the old momenta pi, is equal to new momenta pi plus epsilon times the partial derivative of g with respect to qi, and likewise for the partial derivative of f2 with respect to new momenta pi. Therefore, the change in the old and the new momenta delta pi is equal to minus epsilon times the partial derivative of g with respect to qi, and the change and the infinitesimal change between the new and the old coordinates delta qi is given by epsilon times the partial derivative of g with respect to the new coordinates, which is also equal to epsilon times the partial derivative of g with respect to the old coordinates, where in doing this we have kept only terms, first order terms only have been kept in pi and its derivatives. The function g is called the infinitesimal generator of the canonical transformation. There is an important connection between the infinitesimal contact transformations when the transformation from the old coordinates q and p is made to the new coordinates and momenta capital Q and capital P. To see this connection, consider a change in the function, a function f of q and p as a result of the transformation to the new coordinates capital Q and capital P. Then the change in the function delta f is given by a value of some function evaluated at qi plus delta qi and pi plus delta pi minus the value of the function at the point qi pi. To first order in infinitesimal changes by Taylor series expansion, delta f can be written as delta f is equal to df by dqi delta qi plus df dpi delta pi, and using the transformation equations, then delta f can be written as epsilon times this quantity sigma over I du by dqi dg by dpi plus du by dpi and dg by dqi, that is delta f, can be written as epsilon times the Poisson bracket between u and g. Now, if the function f is the Hamiltonian h, the infinitesimal change in the Hamiltonian then under infinitesimal canonical transformation, there is delta h is equal to epsilon times the Poisson bracket between the Hamiltonian h and the function g. Thus, if G is the infinitesimal generator of the canonical transformation, then the change in the Hamiltonian is given by the Poisson bracket of H with G. That is, the Poisson bracket of H with an infinitesimal generator G gives the change in the Hamiltonian. We have earlier shown that if a function is a constant of motion, its Poisson bracket with H vanishes. Thus, from the equation 2210, we see that a constant of motion generates infinitesimal canonical transformations which do not change the value of the Hamiltonian. In other words, the constants of motion are the generating functions of those infinitesimal canonical transformations which leave the Hamiltonian invariant. The symmetry properties of the system tell us the transformations under which the Hamiltonian of the system remains invariant. We saw earlier that symmetry transformation under space and time translation and under rotations in a three-dimensional Euclidean space do not change the Hamiltonian, and they result in the conservation of energy, linear momentum, and angular momentum. Now, we will revisit this in the form of the canonical transformations which we have discussed. Now, under space translation, the momentum p does not change. That is, delta p is equal to 0, which is epsilon times the partial derivative of g with respect to q, which means that the partial derivative of g with respect to q is 0. And from these equations, we get not only the partial derivative of g with respect to q is 0, but partial derivative of g with respect to p is equal to 1. We get g is equal to p, the momentum of the system. Thus, for infinitesimal space translation, the generator g of the transformation is nothing but the momentum p. If the Hamiltonian of the system is invariant under infinitesimal space translation, then the generator of the transformation, which is the momentum p, is a constant of motion. Thus, p is a constant of motion if the Hamiltonian is invariant under space translation. Now, consider the invariance of the Hamiltonian under infinitesimal three-dimensional rotation. Let under an infinitesimal rotation delta phi, the position vector r changes to r plus delta r. Then this change in the vector delta r, as we have seen on several occasions in the past, is equal to delta phi cross r. That is, a small change in a vector can be related to a rotation. For simplicity, let us consider a rotation about the z-axis. Then delta phi, this change in the phi is along the z-axis. So delta phi vector has components x and y component 0 and the z component delta phi, and the vector r has x, y, z component. Therefore, delta x is equal to minus y delta phi, and delta y is equal to x times delta phi, and delta z is equal to 0. But delta x is equal to epsilon times the partial derivative of g with respect to px, which is equal to minus y delta phi, which in turn is equal to minus y epsilon. Therefore, the partial derivative of g with respect to px is minus y, and similarly the partial derivative of g with respect to py is x dot, and partial derivative of g with respect to pz is equal to 0, and therefore we get g to be equal to x times the y component of p minus y times the x component of p, which is equal to the z component of the angular momentum. So, for the infinitesimal three-dimensional rotation, the angular momentum is the generator, just as the Hamiltonian is the generator. Infinitesimal time translation, angular momentum is the generator for infinitesimal three-dimensional rotation. If the Hamiltonian is invariant under infinitesimal rotation, then the angular momentum is conserved, the result which we have seen earlier too. Now we will discuss Liouville's theorem. In the Hamilton's formalism, as we keep saying, that the dynamical system with n degrees of freedom is completely specified by specifying n generalized coordinates and corresponding conjugate momenta. We can consider a n-dimensional configuration space spanned by these n generalized coordinate axes. A point in the configuration space would then represent a certain state of the system. One can also define a n-dimensional generalized momentum space. in which a point would represent a state of the motion of the system. Thus, each point in the configuration and momentum space represents the position and momentum of the system respectively. The information about the state of the system can be inferred from these points in the configuration and momentum space. But it is, however, more convenient, is possible to define, instead of configuration space and momentum space separately, one can define a 2n-dimensional phase space. Every point in this 2-dimensional phase space would give the position and momentum of all particles of the system. The motion or the curve which traces out in the phase space would represent the dynamical evolution of the system. Thus, if the position and momentum of all the particles represented by a point in phase space is known at any time t, a subsequent development of the system follows a unique path in the phase space. For a macroscopic system, however, which has a large number of particles, for example, if your system consists of gas molecules in a vessel of say 1 liter capacity, this would have roughly 10 to the power 23 molecules. And such an approach, even though can be followed in principle, would be extremely difficult to follow in practice. There are 23 molecules with 3 degrees of freedom each. So phase space is 6 times 23 dimensional. Thus, for a complex system like this, such a procedure is impossible to follow, and the determination of initial conditions for each molecule is well nigh impossible. In such situations, what do? We take recourse to statistical methods. We are not in general interested in such a detailed knowledge of the system as to know its momentum and position at every point. Certain average or the gross properties are all that are required. For example, if you have a gas, we are not really interested in how the molecules of the gas are moving at a given time, where they are and with what velocity they are moving. We may be only interested in knowing the pressure exerted by the gas, its energy, its entropy, etc. We thus consider a collection of particles represented by a collection of points in the phase space. We thus consider an ensemble of equivalent systems. Each point in the phase space thus corresponds to a single system of the ensemble, and the motion of a particular point represents the independent motion of the system. We can then define a density in the phase space. The volume element of the phase space, which is used to define the density, contains a large number of representative points and is yet sufficiently small so that the density may be considered to be a continuous function. The volume element in the phase space, which is spanned by 2n coordinates and the conjugate momenta, the volume element of the phase space is then defined as dV as a product of dq1, dq2, dqn multiplied by d capital dp1, dp2, dpn, where n is the number of degrees of freedom for each system in the ensemble. So you refer to the figure which is shown as a 2-dimensional projection of the phase space in the QI-PI plane. So consider this an element of area dpi dqi in the QI-PI plane in the phase space. Then the number of representative points moving into this area per unit time is equal to the density rho times qi dot. Qi dot is the velocity with which these particles are coming, into dpi plus the number density rho into pi dot dqi. So this is the number of represented points moving into this per unit time from the left and from the bottom. And the number n of systems whose representative points lie with a volume dV is n times rho dV. So the number of representative points moving out of the area per unit time is obtained by the Taylor series expansion of the previous equation. So the number of points moving out is then equal to rho qi dot plus partial derivative of qi of rho qi dot into dqi multiplied by dpi plus rho pi dot plus the partial derivative of rho pi dot with respect to pi into dpi multiplied by dqk. So the number of points moving in is given in equation 22. 18 number of points moving into this phase space is given by 22. 19. Therefore, increase in density in this area in the phase space dqi dpi per unit time is simply the difference of the two, which is equal to d rho by dt dqi by dpi. This is represented by this change in the density in this area element dqi dpi. Dpi is the difference between these two expressions, which is equal to minus of partial derivative of rho qi dot dqi plus partial derivative of rho pi dot dpi multiplied by dqi dpi. And when we sum over all possible values of I, then the equation we get is d rho by dt plus sigma over I of partial derivative of rho with respect to qi into qi dot plus partial derivative plus rho times partial derivative of qi dot with qi plus partial derivative of rho with respect to pi dot plus rho times the partial derivative of dpi of pi dot with pk is equal to 0. Now, using Hamilton's equation of motion, where qi dot is equal to partial derivative of h with respect to pi and pi dot is partial derivative of h with respect to qi, we have dqi dot dqi as the second order partial derivative of h with respect to pi qi, and the partial derivative of pi dot with respect to pi is minus the second order partial derivative of h with respect to pi and qi. Therefore, when we substitute these terms, then the equation 22 becomes d rho by dt plus sigma over I partial derivative of rho p with respect to qi plus dqi plus this quantity which shown in equation 22 is equal to 0, which is the total derivative of rho. Therefore, we have the Liouville theorem that d rho by dt is equal to 0, which states that the density of representative points in the phase space remains constant during the motion. This is an important result in statistical mechanics. We now discuss another important theorem in statistical mechanics, namely the Virial Theorem. Consider a collection of particles whose position vectors and momenta are respectively given by the vector r with a subscript alpha and the momentum p with a subscript alpha. And we assume that the position and momentum vector remains finite at all times. That is, position and momenta are bounded. Now we define a quantity S, which is a scalar product of the momenta and the position vectors summed over all particles alpha. The time derivative of this quantity S with respect to time can be written down, and if we take the average of this quantity over a time tau, then the average of the time derivative of S with respect to t over a period of time tau by definition equal to 1 upon tau integral ds by dt into dt, which is equal to value of this quantity S at time tau minus the value of the quantity at time t is equal to 0 divided by tau. Now, if the motion is periodic, period is tau, then S tau is S0, and in which case the time average of ds by dt is equal to 0. If motion is not periodic, then this average of ds by dt can be made arbitrarily small by increasing tau, since the quantity S is bounded. Thus, the time average of S can always taken to be equal to 0. Now, sigma over alpha P alpha dot R alpha dot is equal to minus sigma over alpha of P alpha dot R alpha. But P alpha dot R alpha dot is 2 times the kinetic energy of the particle, and P alpha dot by the Newton's law is equal to the force acting on the particle alpha. Therefore, 2 times the time average of the kinetic energy is equal to minus the average of force F alpha dot R alpha, which is the work done, and the average kinetic energy is equal to minus half the average of F alpha dot R alpha summed over all particles. That is, the total kinetic energy of the system is equal to the virial of the system. The virial of the system is defined by this quantity half average of F dot R sum over all particles. If the force F alpha is derivable from the potential U alpha, then the Virial theorem is expressed in the form that the time average of the total kinetic energy of the system is equal to 1/2 of R alpha dot the time average of R alpha dot gradient of the potential U alpha sum over all particles alpha. To see what we really mean by this, let's consider a simple example where the particle interaction is a central power force law. That is, suppose F varies as some R to the power n. Then from the Virial theorem, we have average total kinetic energy equal to what? It turns out this is equal to n by 2 into U. For the central power force, F is equal to R to the n. The corresponding potential energy can be written as some constant k times R to the power n plus 1, because the gradient of this will give the force R to the power n. So computing the scalar product of R alpha with gradient of U, this is equal to R into du by dr, which is equal to n plus 1 into U. Therefore, the kinetic energy T average value is equal to n plus 1 by 2 multiplied by the average potential energy. So the Virial theorem in the presence of a central power force takes the simple form that the total kinetic energy of the system is equal to n plus 1 by 2 times the total potential energy, where the force changes as R to the power n. Now for gravitational force, which is the inverse square force, n is equal to minus 2. So substituting n equal to minus 2, we find the total kinetic energy is minus half times the potential energy. And for a linear interaction where n is equal to 1, the total kinetic energy is equal to total potential energy. Whereas for the inverse cubic interaction, n is equal to minus 3, the total kinetic energy is equal to the negative of the total potential energy. Let us now summarize what we have learned in this module. We have learned that the generating functions of an infinitesimal transformation which leave the Hamiltonian invariant is a constant of motion. So all those generating functions of infinitesimal transformations which leave the Hamiltonian invariant are constants of motion. We learned that energy, linear momentum and angular momentum are the generators of infinitesimal transformation under the time translation, space translation, and under three-dimensional rotations respectively, and are conserved. Thank you.